Hey everyone, in this video, let's take a look at question 496, next greater element 1 on Leetcode, part of our blind 75 list of questions. So let's begin. In this question, I'm actually going to go ahead and just copy the examples here. I find that they're easier to understand than the actual question. Phrasing is a little weird. So in this question, we're given two arrays. We're given a nums1 and a nums2. You can think of nums2 as the entire array, and nums1 is basically telling me which of the elements in nums2 I want to perform this next greater element operation on. What is the next greater element? The next greater element is the element of which, for example, if I ask for the next greater element of 3, it is the element to the right hand side of 3 that is greater than 3, and it is the first of that element. So in this case, it's going to be 4. It's possible there's like 6 and 7 here, but we only take the first one into consideration, which is 4 here. Now, this basically tells us like for which element we want to look this up. So you can see here, for 4, there is actually no next element, so that's why we return a -1. For 1, the next element here is a 3, so we return a 3. And again for 2, there's nothing, so we return a -1. What about the next example? Well, in this example, we have 2 and 4 that we're looking for. The next element of 2, next greater, is a 3. For 4, again, we don't have anything, so that's why we return 3 and -1 here. Okay, so the question is like phrased a little bit differently, so hopefully the examples illustrated what the question is really about. But if I just gave you like this array here, right? If I just gave you this array here, how might you go about finding the next greater element of all of these? Like, what if I just want to find the next greater element of 1, 3, 4, and 2, and then maybe I can like store that somewhere, and then in from nums1, I can just look that up, right? So here I can see that for 1, the next greater element is 3. For 3, it's 4. 4, it's -1. For 2, it's -1, right? And then once I have this information here, then I can basically just loop through my nums1, and then I figure out, okay, so for 4, I want to add in -1 to the array. For 1, I want to add in 3 to the array. For 2, I want to add in -1 to the array. Maybe let's start with that type of approach. So we have nums2, and basically we will find the next greater element for all of the items in nums2, and then in the very end, we can just perform like a hash map lookup to map the indices, or map the items here to the appropriate answer here. So let's take a look at how we can do that. Well, if you think about this question, how would you go about like finding the next greater element, right? So let's say I'm on number 1 here. Well, what I would need to do, and maybe this is kind of more obvious if I have like a larger array, maybe like 4, 2, 7, 8, something like this. If I'm on number 1, what I need to do is I need to look on my right hand side, and for the first element that is greater than number 1, I will store that as my answer. So in this case, it's 3. When I'm here, what I would do is I would look on the right hand side here, and I will store the answer such that it is the element that is the next greater one from 3, which is 4 in this case. Then I start off at 4, and then I can see the answer is 6. You can see this is actually a slow algorithm because we're doing a O of n squared time lookup here, because we're looping basically n squared times here. But maybe we can start off with that and see where we can arrive at. So let's maybe go ahead and start off with that. So what I can do here is I can go through the items in nums2. So I would do for I in range 0 to length of nums2, and then I would do for j in range. Start from I, and then it'll go to length of nums2, right? So maybe like we start off I over here, I will start off here, j will start off here, and j will basically look here, look here, look here, look here, and look here. Okay, so what I want to check now is I can check if nums2 at j is greater than nums2 at I, well then I found my element, right? So I can basically just record this. So I will first of all go ahead and break because I don't want to look further in the loop. I only want to return the first one. So we have that information here. So now we store the element, right? So next greater, initially we can say it's -1, assuming like we find none of these. But now we will store it. We will say next greater is equal to nums2 at j. And then once this j loop is completed, then now I know that for 1, the next greater element is 3. So then I can actually create this in a map. I can record this information in a hash map. So then I can just do like, let's just call it D for dictionary, right? And then what I will do here is I will store D of what? Of nums2 I is equal to what? Is equal to this location, this next greater element here, right? So that's basically what we have. So let's just maybe go ahead and try to see if this works. So here I would just return an empty string. But let's just maybe see that it works with the first example is this one. Okay, so let's just see that it works. So we can figure out at least like what is the next greater element. So we can see that for 1 we get 3, for 3 we get 4, for 4 we get -1, and for 2 we also get -1. Perfect. So now that we have this information, all we need to do is when filling out our result array, like our final array, we will go through nums1. So for num in nums1, we will figure out what is the answer based on nums2. So I can do res.append d at num. And then in the end, I can just return res. Let's take a look at this. Go ahead and run this test case. And you can see it giving me the right answer. I'll go ahead and submit it. And also we get the right answer. Now, this is actually faster than 94%, but it really shouldn't be because this is an O of n squared approach. It's not necessarily the best one here. The best one is something which we call a monotonic stack. And it's maybe something you haven't learned before. So let's spend some time discussing what a monotonic stack is. And so then we can figure out how we can actually just not loop n squared times here, but figure out the answer in just one go in O of n time. So let's take a look at how we can do that. Open up my paint here. And I've already have something set up. So here's my monotonic stack. What is a monotonic stack? It is essentially a stack that is either strictly increasing or strictly decreasing. That's what monotonic means. It means strictly increasing, strictly decreasing. In the types of questions in which you're asked to find the next greater, then you want to use a decreasing monotonic stack, which basically means the items in the stack will all be decreasing, maybe like 5, 4, 3, 2, 1, etc. In the questions that you're asked to find the next smaller element, you will find or you will use an increasing monotonic stack. Okay? Basically, that's the idea of like how you want to use this or how you want to understand to use it. Here I have a set of numbers 5, 1, 4, 2, 3, 6, and here I've written down their next greater element. So next greater element 5 is 6, 1 is 4, 4 is 6, 2 is 3, 3 is 6, and 6 does not have 1, right? And here I've basically just printed out all of the elements here. What do we do in a monotonic stack? Well, in a monotonic stack, first thing you do is you actually go through and you want to add the elements to the stack, but you want to add them such that you're preserving the decreasing stack property. What do we do here? Well, first thing we do is we add in the number 5, because there's no problems around the 5. What about next? We add in the number 1. Can we add this? We can, because it's still a decreasing monotonic stack. Because you can see 5 and then we decrease to 1. So it's all good. What about now? 4. Can we add in 4? We can't add in 4 because if we were to add in 4, then it would break the monotonic stack property. It would be decreasing and then increasing. What do we do? Then we go ahead and we pop 1. And then we can see, can we add 4 now? Okay, yes, we can add 4 now. So we'll go ahead and add 4. Now notice what happened here. When I popped 1 from here, what does it necessarily mean? Well, if you think about this really carefully, it means that the item that I'm popping, the next greater element must be the item that I'm inserting. It has to be, right? Because we're going to the array in order. I'm popping this element. It's greater than, which means it defeats the purpose of a decreasing monotonic stack. And so the next greater element of 1 has to be 4. And so you can actually see here that we have exactly that. The next greater element of 1 is 4. Okay, so let's continue. So we've added in 5, 1, and 4. Can we add in the 2? We can. There's no problem there. Okay, so we add in the 2. Now what about a 3? Can we add in a 3? We can't because it's greater than 2. So we pop the 2. And because we're popping the 2, we learn or we know that the next greater element of 2 is equal to 3. And so we can see that right over here. Why is that the case? Well, because we know that when we're popping, the next element must be greater. And because we're going in order, then the next greater element must be the item that we're just about to insert, which in this case is 3. So insert the 3. Now what? A 6. Okay, in the case for 6, can we add it in? We can't, because 3 is less than, so it'll break the structure. What do? We pop the 3, and then we understand that 3's next greater element must be 6. But notice how we can also pop this. We can also pop 4, and we can also pop 5. So we pop 4, and 4's next greater element is 6, and we also pop 5. 5 next greater element is also 6. So notice how by using a monotonic stack, we're able to determine what the next greater element is, specifically using a decreasing monotonic stack. Let's take a look at how we can do this in code. So go ahead, and I'll actually just remove this information that we have here. Okay, so now let's take a look. And there's like a general type of structure you want to follow with these types of questions, but let's take a look at how we can do this. First of all, what we can do is we can find our stack. And what we need to do is we need to go through the nums2, right? We need to go through the second array. I will do for I in range 0 to length of nums2, right? Now, what? Well, let's just assume that, we're in the middle somewhere, right? Like, let's assume that we already have items on the stack. Like, maybe we have 5 on the stack. maybe we have 1 on the stack, right? And now we're looking at number 4 here, okay? We're looking at number 4. So what do I want to check? Well, I want to make sure that I am only strictly decreasing, right? So assume items on stack, maintain decreasing stack. So we want to maintain this decreasing order. So what can I do here? Well, I want to check the case in which I can pop elements off the stack. Here I can check if I can pop. So can I pop? So how can we check if you want to pop? Well, in order for us to even determine if we can pop or not, first of all, the stack has to exist, right? So there has to be items left on the stack. I can do while stack and what? Well, then I need to check that the last element on the stack, if it is potentially less than the element I'm about to add, then I know that I can pop it. Then I can do and nums2, or actually I can just do stack at -1, right? So this will be the last element. If this is less than nums2 at I, if this is less than the number I'm actually adding on, then I know that this is not a valid order. So I have to pop this. What I would do is I'll go ahead and pop like item, and I can do stack.pop. So this will effectively like remove the 1 here when we're about to add in the 4. So it'll remove the 1. And now, so what do I know? So I know that this item that I just removed, its next greater element must be this. So then I can basically store in my array. So I can do t at item, its next greater element must be nums2 at I, right? So this is the case in which I want to pop. Let's say I don't want to pop and I just want to add to the stack. Well, I can very easily do that. I'll just do stack.append, and I will append the number. I'll do nums2 at I. And that's basically all there is to it. In the very end, we might still have items left on the stack. And so what we can actually do, because in this case, if you take a look at it, in this case, after we process all of this, 6 was still left on the stack, right? So we can just take a look at that. And what we can do is while still stack, right? While stack, then t at stack.pop is equal to -1, right? Because there are no more elements to the right-hand side of it. So we can do that. Okay. That's basically all we need here. And then this remains as it always does. Let's try to go ahead and test this to see if we run into any problems. And res is not defined. And I did not define it here. So res I will define here. Okay, and let's go ahead and submit. Okay, perfect. It works. So this is an O of n time algorithm. And this, we're using a monotonic decreasing stack. In the next set of problems, we might use an increasing one, etc. But the concept is the same. Okay, so it's O of n time algorithm and also O of n time space because we have to add to the stack. All right, I hope this helped.